Hi everyone, today we have a talk by Aparna, and she will talk about algebraic topology, and she will give an introduction to simplicial sets.
Thank you. Thank you for the introduction. Yeah, so I'll be talking about simplicial sets and keeping it as leisurely as possible. So the notion of simplicial sets came from simplicial complexes, which are some spaces that people study in topology and algebraic topology. And so we'll see what those are first before going into simplicial sets. So simplicial complexes are spaces that are built sort of combinatorially, like you have some basic building blocks and you take a bunch of them and you glue them in a nice manner to get these spaces. And they're pretty nice because they cover a lot of spaces in topology, and they're also very easy to study. So these are the building blocks that I was talking about, these standard n simplices, which is the set that I mentioned. But if you unwind the definition for some lower ends, so for 0 you get a point, and one simplex is a line with 2 points on the boundary, and 2 simplex is a square is a triangle. So what you do is you take 3 points which don't lie on the same line, and take the smallest convex set which contains all the points. And similarly, you get your 3 simplex by taking 4 points and then taking the smallest convex set containing them. And these are your building blocks, and you're going to glue them in some way. And to understand how we're going to glue it, we need to know what the face of the simplex is. And if you notice each of these standard simplex, the boundary is made up of n-1 simplices. So the 2 simplex the boundary of the 2 simplex is made up of 3 1 simplices. And for the 3 simplex, there are 4 2 simplices which make up the boundary. So each of these n-1 simplex on the boundary is called the face of the simplex. And what we do is we take these simplices and glue them along their faces. So the definition goes this way, that a simplicial complex is a set of simplices. So you have this giant collection of simplices such that every face of a simplex in the collection is also part of the collection. And any non-empty intersection of these 2 simplices is a face of both of those simplices. So this second point just tells you how the gluing happens. And like a typical example would be something like this, where you can see how the 2 simplices are being glued along their 1 simplex face, and you can also glue them along their vertices. Okay, so one way to describe a simplicial complex was the definition that I mentioned, where you give a collection of simplices which satisfy those conditions. But there are better ways to describe this space. So namely, I can give you the set of simplices in a much better way. Like I can give you for each n how many n simplices you have. So for this case, this is what you'll get. And since we said the face of n simplex should also be part of the simplex, part of the collection, we also have the faces of the 3 simplex, part of the 2 simplex, 2 simplices, and so on. And now I need to tell you how the gluing happens. And for that, we use these maps that we call the face maps. So what the face map does is, say the face map from 3 simplices to 2 simplices takes a 3 simplex, and it gives maps it to one of its faces in the set of 2 simplices. So since each 3 simplex has 4 faces, you would have 4 face maps from x3 to x2, and similarly for from x2 to x1 you have 3 face maps and 2 face maps for all the edges. And so this is a way to describe a simplicial complex. And what people thought was, okay, let's just take the fun out of all of this. Let's forget about the pictures. Let's forget about the geometry, and just take out the algebraic data of this, and let's see what we can do with that. So that gives us simplicial sets. So a simplicial set is a collection of these sets, xn's, with certain maps, which we call the face maps and degeneracy maps. And I didn't talk about degeneracy maps before because they don't really mean anything geometrically. What degeneracy map does is it increases the dimension of the simplex, but it doesn't really change the simplex. So for instance, you can take a 2 simplex and collapse one of its edges and see it as, get back a 1 simplex. So it really is a 1 simplex. Geometrically, it's just a line, but if it might belong to the set of 2 simplices. So its dimension is different. So the algebraic data associated with that simplex is different. So yeah, picture-wise, it doesn't matter, but we do need to include this when we're talking about the algebra. And we also require them to satisfy certain axioms, which if you go back to the example of simplicial complexes, they seem pretty obvious, all of these. So it is sort of amazing to me how people boil down the geometry that's going on in the gluing of simplicial complexes to just these 5 axioms. Okay, so this is a definition, and this is not pretty good because it's not that nice because you have all these axioms that you need to probably go back to every time. But the language of category theory gives us a better definition and a more compact one. So let's see what that is. So a brief introduction to category theory. So in mathematics, you always come across mathematical objects and a relation between those mathematical objects. So you can take sets, and then the relations would be functions. If you have vector spaces, the relations would be linear morphisms, and so on. And categories give a nice way of like packaging that information along with all the other constructions that you do with these objects. So a category, usually it consists of a class of objects and a class of morphisms between any 2 objects. So in case of sets, your objects would be sets and morphisms would be functions. And along with that, you need to tell me how the morphisms compose with each other. So if you have a situation where you can compose the morphisms, like if you have a map from X to Y and then another map from Y to Z, you should be able to get a map from X to Z. And you also need to choose an identity morphism, which is a map from an object to itself. And these should satisfy some very like bare minimum properties, like the composition should be associative, and the identity should be like the identity for the composition. So this gives you what we call a category, and usually. Categories, the objects are sets, and morphisms you would take like the appropriate functions. So for instance, if your category is groups, then the objects would be groups, and morphisms would be group homomorphisms, or vector spaces, objects would be linear vector spaces over the field K, and morphisms would be linear morphisms. And top is the category of topological spaces with morphisms, continuous maps. But your objects might also not be sets, so there is no notion of functions between them. And yeah, in those cases you get in those cases you would have to explicitly tell what a composition is and what an identity is, and it's not usually obvious what you should do. Okay, now we defined a mathematical object. We need to say how they interact with each other. So they interact through functors. A functor is a function between the respective class of objects and morphisms. So it takes an object and maps it to an object in the codomain. It takes a morphism and it maps it to an appropriate morphism. So if it's a morphism from X to Y, then it maps it to Fx, Fy. And since we have this structure of composition on our morphisms, this functor better respect that structure. So it should commute with composition, and it should also respect the chosen identity for each X. And then we have this notion of contravariant functor, where everything remains the same, but the direction of F switches. So it maps a map from x to y to a map from fy to fx. And this happens in a lot of situations in mathematics. So it's okay to give it a name. Okay, coming back to simplicial sets. So this is the category that we're going to consider, where the objects are finite sets. So you have this set of numbers from 0 to n for each n, and the morphisms are going to be order-preserving maps from m to n. So we're not taking all functions from m to n, we're only taking order-preserving maps with the usual composition of functions and the identity map. And this works out because the composition of order-preserving maps with order-preserving maps is, again, order-preserving. Okay, and if you look at this category closely, and if you see how the maps, there's not a lot going on between two consecutive numbers. So the maps between, you can list down the maps between two consecutive numbers. So I've listed it down for some initial cases. So for instance, from 1 to 2, you have 3 maps going from 1 to 2, and you have 2 maps going from 2 to 1. So the maps on the top are called co-degeneracy maps, and the maps on the bottom are called co-phase maps. And any other morphism in this category can be written as some combination of these consecutive maps. So in a way, these maps generate the set of morphisms in the simplex category. And now we can have a better definition of a simplicial set, with that it is a contravariant functor from the simplex category to sets. So the op on the triangle just means, on delta just means that it's a contravariant functor. So what do we do? What does a functor do? It takes n and it maps it to a set xn, and then it takes all of those co-degeneracy and co-phase maps, and it maps it to the appropriate, maps it to a map between the appropriate sets. And these are the maps that we call the phase and degeneracy maps. And this is indeed enough to define a functor from the simplex category to sets, because any other map is generated by the di's and si's, and you can just, since x commutes with composition, it all works out. So is it the same as the definition we had before? It is, because the d upper I and s upper I satisfy the simplicial axioms that was mentioned. So x of d upper I and x of s upper I will also satisfy the simplicial axioms. So we do get back the definition that we talked in the beginning. Okay, so how do simplicial sets interact with each other? So a morphism of simplicial sets is a map, is a collection of maps going from xn to yn. And again, we have extra structures on our xn, so it just has to respect the extra structure. So the phi n's and phi m's should make this diagram commute for every f in the set of morphisms on the simplex category. And since f is generated by the co-phase and co-degeneracy maps, it's also enough to check on these, check on just those maps. Yeah, so this also makes it into a category. So you do get a category of simplicial sets where the objects are simplicial sets and the morphisms are precisely the one defined here. Okay. Yeah. So let's look at some examples. So the first example is a total singular complex of a space. So we're going to construct, given a topological space, we're going to construct a simplicial set out of it. So the zero simplices are continuous maps from the standard zero simplex to y. And the standard zero simplex was just a point. So this is just like points of y. And the one simplex is a continuous maps from the standard one simplex to y, which the standard one simplex was an interval. So these are just paths in y. And similarly, in this fashion, you can define an SYN. Okay. And the phase and degeneracy maps are the obvious ones. So I've written down a couple of examples. what you do is you take a map from the 2 simplex to y and you pre-compose it with the inclusion of an edge if it's a face map, and otherwise you pre-compose it with the collapsing of an edge if you're going to talk about a degeneracy map. And with all of this, these maps satisfy the simplicial axioms and you get a simplicial set. And yeah, so moreover, you also get a functor from the category of topological spaces to the category of simplicial sets. So to get a functor, you need to tell how the continuous map, you have to map any continuous map from x to y to a simplicial map from sx to sy. And again, it can be done in, it's like similar to this. You just have to compose it with the map. Okay. So a natural question would be, is there something you can do in the other direction? And if you can do something like that, does it give you some sort of an inverse? So you can do something in the opposite direction, but it doesn't give an inverse, but it does give a good thing, which is a left adjoint. So let's see what a left adjoint is. Okay, so you have a lot of notions of sameness in categories. So first you can have equality, where C is equal to D, or you can have isomorphisms. And when you come down to the level of equivalence of categories, you really are, you really start using the philosophy of category theory, which is that you look at the morphisms, or the morphisms are the important thing that you need to look at rather than the objects themselves. So from inequivalence of category, you really ask the morphism sets to be the same, but you can be a bit relaxed on the objects. And then finally, below equivalence of categories, you have this notion of adjoints. In one form, you can say that having an adjoint means that there is some subcategory which is equivalent to a subcategory of the codomain, which you can say it is on some level of sameness between categories. But anyway, this is the definition that is usually used. So you say that F has a right adjoint if this relation is satisfied. Probably should remind you of some adjoints with inner products, and I guess that's where the name came from. But this is pretty nice to have, and we'll see maybe one reason why today. Okay, so we can define the adjoint of the total singular complex as, we can just define the geometric realization as the left adjoint of the total singular complex. But this is also a much better, this is a much better way of defining geometric realization. So you take a simplicial set X and you want to get a space out of it. And the topological space that's been defined is very similar to how you would construct the simplicial complex when I gave you the initial informations in the beginning. So like I gave you a set of n simplices, and then I gave you the face maps, and I told you how the face maps would tell you how to glue them, and that's exactly what you do. So for each point in Xn, you put out a standard n simplex, and you have this giant disjoint union of simplices, and then the equivalence relation tells you how the gluing happens and what are the faces that you need to collapse. And this is this gives a functor from the category of simplicial sets to the category of topological spaces. And as claimed before, it also gives an adjoint for the total singular complex functor from the category of topological spaces to simplicial sets. And this is pretty good, and to understand why it's nice, you have to know some things from algebraic topology. So let me do a quick introduction to that. So one of the biggest problems in topological spaces is the characterization of spaces. So given two spaces, when are they the same, or when do you see them, when are they the same or when are they different? And one nice thing that people have constructed are these things called algebraic invariants, which are properties that you can associate with a space, and it wouldn't change with an isomorphism or a homeomorphism. So the study of algebraic topology, so in algebraic topology, you basically construct these algebraic invariants. And today, one such invariant or a bunch of invariants are these groups called homotopy groups. So what we do here, and again, one big invariant with spaces is the holes in the space. So in this, with these homotopy groups, you can easily detect these holes. So what you do is you can put a loop in a space, and you can see if you can contract it to a point. And if you can contract it to a point, it means that there's no hole inside the loop. But if you were not able to do it, then there's something going on inside, and there might be a hole inside. So that is the basic idea behind these definitions. So so instead of just contracting, you can also ask if you can deform a loop into another loop. And if there's a problem in doing that, then there's something going on in the space in between. So you can take two loops, f and g, which is just maps from the circle to x. And you say that f is homotopic to g if there exists some kind of continuous deformation from f to g. So h is a continuous map from S1 cross I to X, and at time 0 it is F, and at time 1 it's G, and in the middle it's just some loop with the same starting and ending point. And if you're able to find such a continuous map which goes from F to G, then though we say that those two loops are homotopic. And in case of contractible, you can take your second loop to be a point, the constant loop. And if you're able to take a loop to a point, then we say that that loop is contractible. Okay. And this relation between loops is an equivalence relation. So you can take the set of all maps from S1 to X, which sends the like you have a chosen base point from S1 and you have a chosen base point from X, and you always make sure that the base point has been preserved. So you take all of such maps and you quotient out by the equivalence relation of homotopy, and what you get is called a fundamental group of X. And this again, a fundamental group is not enough to determine a space. For one, we are just looking at loops, which sort of is one-dimensional, and there can be some weird things going on in two-dimensional or in a higher dimensional places. And also, when you're taking loops up to homotopy, usually the homotopy is not canonical, or there's no the chosen homotopy. So you might end up like losing information by just considering loops up to homotopy. So for instance, if you look at the sphere, and if you look at the pink circle as your loop, you can contract it to a point using the bottom half, or you can contract it to a point using the top half. And in fact, any loop on S2 can be contracted to a point. So and it's also true for a plane, like a plane R2. But we clearly know that S2 and R2 are not the same, or they look completely different. And S2 has like a two-dimensional hole in it, which has not been detected by loops. So we factor that in, and we define the second homotopy group as these maps from S2 to the space X, quotiented out by the homotopy relation. So this sort of homotopy can be defined for any continuous maps. So you can deform any continuous map. You can ask if any continuous map from X to Y can be deformed into another continuous map from X to Y. So again, so we're doing the same thing here. So a deformation, it's the second homotopy group is given by the maps from S2 to X up to homotopy. And yeah. And again, this is not enough to determine our space. Again, we're just restricting ourselves to 2 dimensions, and a lot of information is lost by just looking at the homotopies. So by just looking up to homotopy. So we continue this process, and we get pi n for each n greater than or equal to 0. So for n equal to 0, you would have S0. S0 is just 2 points, two disjoint points, and in that case, pi naught will just turn out to be the path components of the space. Okay. So does all of these groups determine space? Yes, I mean, if loosely speaking. So there are these very nice spaces called CW complexes that, and these are all the spaces that homotopy theorists are concerned about. These homotopy groups do determine the space for CW complexes, but you generally do talk only about CW complexes. Okay, so what does this have to do with simplicial sets? Well, simplicial sets have a geometric origin, so you can start to think of simplicial sets as spaces, and you can have this definition of homotopy for simplicial sets as well. So to do that, you first need to define products of simplicial sets, which is defined pretty naively. Like you take the n simplices of x cross y will just be xn cross yn, and then you can similarly define the phase and degeneracy maps. And then you can take the simplicial set whose geometric realization is the interval as your I, and you can now define a homotopy between homotopy for maps between simplicial sets. So it tells you how a map between a simplicial set sort of deforms into a map, into another map between simplicial sets. And then you can also define this notion of sphere, a simplicial sphere, which would just be, you could take your n standard simplex, you could just take the boundary of the n standard simplex, and you can look at the simplicial set whose geometric realization is this boundary of n standard simplex, and that would act as your sphere. And that way you could also define the homotopy groups for each n, which is, again, the homotopy in this case is not an equivalence relation in general, but in the situation that we are talking about, it is an equivalence relation. So the adjoint property that we had before really says that for any space, the homotopy groups of that space coincide with the homotopy groups of the singular complex associated with that space. So if you want to know your the homotopy groups of this space Y, it's just enough to look at the homotopy groups of SY. This is particularly nice if you want to study about spaces, but you don't want to deal with geometry or pictures, and then you can just jump to simplicial sets and work with some abstract nonsense. But again, and a lot of people do that. Like whenever convenient, people do jump to simplicial sets and come back to topological spaces when they need some pictures. So if you hear a homotopy theorist talking about spaces, 50% of the time they are talking about a simplicial set. And this adjoint also says something more. For one, it also says that the constructions, so like you can do other constructions on simplicial sets using the notion of homotopy, like homotopy limits, co-limits, and this adjoint says that all those also play out nicely with the corresponding topological notion of homotopy limits and co-limits. And moreover, or more importantly, these definitions also have this also give you this model structure on the category. So you have a model structure to do homotopy theory on the category of topological spaces. And these definitions give a model structure on simplicial sets to do homotopy theory. And this adjoint also says that these model structures coincide. So if you want to do homotopy, if you want to extend the ideas of homotopy theory to other parts of mathematics, you don't have to deal with topological spaces. You can just work with simplicial sets, which is a much simpler category, and it's easier to control and easier to understand. Now, so we have seen how simplicial sets can be seen as spaces or closely related to spaces. Now, they're also closely related to categories, which we'll see now. So we can define this category of which we call the fundamental groupoid of X, where the objects of the categories are points of X, of the space X, and the morphisms are paths from X to Y up to homotopy. So if two paths are homotopic, you just consider them as one. And this, along with the composition, so the composition you define here is you take, so you have two paths you have a path from X to Y, and then you have another path from Y to Z. Then the composition would be the concatenation of this path. So one way to concatenate them is go through the first path with twice the speed and then use the remaining time to cover the second path. So that is a concatenation of, or that gives us a composition of morphisms in this category, and identity is just the constant path. And this gives it a category, and this is much better than the fundamental group, which was discussed. For one, it doesn't depend on some choice of base points, and it also has more information than the fundamental group. So first of all, you can get the fundamental groups out of this category. If you look at the maps from X to itself, if you look at the paths from X to itself, which are just loops, you get back your fundamental group. You get back fundamental group of the space, and it also has the path components of the space in it. If you look at the isomorphism classes of the objects, that gives back the path components. So this category has more information encoded in it, and the language of categories just gave us a better way of encoding or packaging all of these information. So, but we just saw that SY has all the information that you need about a space. You can, so the natural question is SY a category, or better, to what extent is SY a category? And here we have to see the links between a category and simplicial sets. Okay, so one way is easy. So given a category, you can define a simplicial set. So what you do is you take the 0 simplices as the objects and 1 simplices as the morphisms, and 2 simplices would be pairs of composable morphisms, and similarly n simplices would be n morphisms which can be composed. And the degeneracy and face maps are defined obviously. So for degeneracy, you insert an identity at the ith position, and for face map, you compose the map which goes into CI and comes out of CI. And at the terminal position, you just forget about the map, and yeah, you get a smaller simplex. And all of this gives a simplicial set, and it also gives a functor from the category of categories to the category of simplicial sets. And again, so nerve is just a very complicated way of describing a simplicial set, describing a category. It determines a category up to an isomorphism, and also it has all the information that you would need to describe the category. For instance, the 2 simplices give you how the composition works, and the degeneracy map from C1 to C0 gives you the degeneracy map from C0 to C1 gives you the identity maps. And yeah, so it's just a more elaborate way of defining a category. So now, given a simplicial set, how do you get a category out of it? And you can do that by using the inspirations from nerve of a category. You can take your objects to be the zero simplices. You can take your morphisms to be the one simplices. And the two simplices are going to talk about the composition. So if you have a two simplex like that, which goes from F, you have these morphisms F, G, and H, and you have a two simplex, you can say that this two simplex acts as an identification between the composition G, F, and H. So in other words, you can say that H is equal to GOF, and the two simplex sort of witnesses the composition or the equality happening. But there are some problems with this idea because, first of all, our two simplex, the two simplex that we need for every composable pair of morphisms, we might not have the two simplex. It might not exist. And you can solve that problem by just putting it in your assumptions. So whenever you have a situation where you have a morphism, where you have two composable morphisms, you should be able to complete it to or extend it to a two simplex. The next problem is even if you assume it to be even if you assume it to exist, it might not be unique. But if you think about it, it's a bit you can assume it to be unique, but it's a bit unnatural to do so because, for instance, if you go back to the example of fundamental groupoids, the composition, as I explained, was the concatenation of paths. And I said you go twice the speed on the first one, and then you take the rest of the time to cover the second path. But that was kind of arbitrary. Like I can travel the first path with thrice the speed and then take the rest of the time to travel the second path. And luckily, these two descriptions are homotopic, so they do give us the same composition in case of fundamental groupoids. But if you're going to impose the condition of uniqueness, then you should have a unique way of concatenating these paths, but there's clearly no better way of doing it. Like going 2 times or 3 times is not, there's no well-defined better way of doing the concatenation. So it's more natural to not assume uniqueness, but to have some way of identifying the instances of composition. So in case of fundamental groupoid, we had homotopy, so we can ask something like this. And simplicial sets, the formalism of simplicial sets give us a nice way of doing that. So if you have two compositions for F and G, that's H1 and H2, and if you have a 3 simplex which has these two simplices as a face, and you were able to complete the 3 simplex, then you can say that 3 simplex acts as an identification for this composition. And so now you know a way to identify the compositions. But again, we run into the same problem that this 3 simplex might not exist, and even if it does, it might not be unique. But you can argue similarly again, you can assume existence, but you cannot assume uniqueness because it's unnatural. Like it is like assuming that 2 paths have a unique homotopy, which doesn't have to be true. So again, you would have a similar situation, and you keep doing this for all n, and you end up with this notion of quasi-categories. And SY, the total singular complex that I mentioned before, is a quasi-category. And quasi-categories acts very much like a category, but it's not a category. It has all the constructions that you can do on a normal category, like limits, colimits, Kahn extensions, adjunctions, and everything. But it is more free, and you do not have, you don't have to worry about equality. You just need to have some sort of an identification. And so simplicial sets give a way to, so simplicial sets, or the particular simplicial set here, where these conditions are satisfied, also acts as a category or somewhere close to being a category. So if you're ever in a situation where you need something which looks like a space or acts like a space, but also acts like a category, then simplicial sets or quasi-categories would help you out. Yeah, so that's all I wanted to talk today. And yeah, thank you so much for the opportunity. I'll be around if you have any questions.